accumulation of the previous area. For example, when I find the area from 2 to 3, that's -1, but when I find the area from 2 to 4, I get -1.5 because I added from 2 to 3 to 3 to 4. So it's an accumulation. It's an accumulation. All right. Because a of x is a function, we know that every function has a maximum and a minimum on a closed interval. In addition, a function can be represented with a graph, and therefore a graph has extreme values, which are where it turns, or think of it as the maximum or the minimum, relative max, relative min. There are also concavity, which we can use, which determines where the graph opens up or where it opens down. More specifically, where it's concaving up, concaving down. And then inflection, which is where it changes its concavity. So to do so, we need to be able to find the derivative of this area function in order to help us find the extreme values. Once again, a is a function, therefore it can be represented with a graph like that, right? And so since it's a function, we want to know where are the extreme values and where is the inflection point. Also, where is the graph concaving up or concaving down? So this would be concaving down, right here, concaving down. And then from here to here would be concaving up. And we do that by analyzing the first derivative and the second derivative of our area function. Therefore, it's important to know how to find the derivative. Now, so let's do that right now. Let's see how we find the derivative of a function defined by an integral. Find a formula for the area function. So, a prime, if I take the derivative, so what I do is I take the derivative of both sides. So the derivative So I want to find the first derivative, or I want to find the derivative of a because I want to be able to find the extreme values. The derivative of a, which is the left side of this equation, can be simplified, or another way to represent it is to write it as a prime, which is the first derivative. And now we go ahead and we find out what is the derivative of a by simplifying the right side. Now, to simplify the right side, this is the left side, the right side. To simplify the right side, I'm going to begin by using the fundamental theorem of calculus, part 1, to evaluate this expression first. And I'm going to leave the result in here. Okay. The fundamental theorem of calculus part 1 says that we can evaluate the integral by finding the antiderivative of the integrand, which is going to be t to the third over 3, and then evaluate that at the two endpoints. So, leaving the derivative symbol alone for now, I now plug those in. So I get x to the third over 3 minus 3 to the third over 3 And finally, I take its derivative to find a prime. So take the derivative of this, that gives me x squared. Take the derivative of that gives me 0. So a prime, which is the first derivative of a, is x squared. So perhaps I can go over here, or I'll finalize the answer here. So the derivative of a prime is x squared. All right, that's it. That's the first derivative of this a function. Okay, so once you have found the first derivative of the a function, then cover up the original function and just work with the derivative to find the critical points and also to find the location of the relative max or the relative min. Don't look at this until you ask for something else, otherwise you might confuse yourself. Now, so if you look back at the original problem, the first derivative is already somewhere in here. You don't have to, we could do all this work to find the derivative of our a function, or we can just identify that, hey, the first derivative is kind of like similar to this term, which we call it the integrand, right? The only catch is that we replace the letter x for the letter t, as you can see, and that's the first derivative of our function that's defined by an integral. And that is the beauty of the fundamental theorem of calculus part 2. Remember that a theorem is a rule that kind of helps us skip all that helps us kind of take a shortcut, and that's what a theorem is. Now, this is going to be true all the time, and therefore we summarize this in a theorem so that we don't have to do this every time. So the fundamental theorem of calculus part 2 is very simple and easy. It says that if you have a function that is defined by an integral, then the derivative of that function is just the integrand. It's just the f function, whatever is inside, whatever the function is after this integration symbol. But there's one catch. The only catch is you replace the variable t with the variable x, and that's the only catch, just like what I did. That's the fundamental theorem of calculus part 2. So here's another look at it. The derivative of the integral, of the definite integral, of an integral function is just the integrand. It's just the function that's inside. But there's just one catch. Replace all the t's with x. Okay. So that's the fundamental theorem of calculus part 2. Let's use it to find the derivative of functions defined by an integral. So here's the first one. So let's find its derivative and let's evaluate these values. By the fundamental theorem of calculus part 2, we know that a prime of x, which is the first derivative, is 1 plus x cubed. Replace the t with the letter x, and that is it. That is the derivative. The inside function is the derivative. Now, you might be curious, does the lower limit value have anything to do with the first derivative? And the answer is no. It doesn't matter what this lower number is. Okay? It could be 10, it could be 0, it doesn't matter. But the derivative is just the integrand. Replace it by the upper limit. And the upper limit has to be a variable. So, that's the first derivative. We're going to go and plug 2 in and 3 in and see what the value is. So plug 2 in, I get 2 raised to the third. That becomes 8 plus 1, that becomes 9, so therefore I get 3. A third, that is the square root of 1 plus 3 square. 3 squared is 9 plus 1, that gives me 10, so that's the square root of 10, and I'm done. The main purpose is to show you how to find the derivative of a function defined by an integral. The fundamental theorem of calculus part 2 says that it's easy. Its derivative is just the function inside. Replace it with the letter x. So, evaluate this expression. That expression is equal to, which stands for the derivative, is equal to the function sine, according to the fundamental theorem of calculus, replace the letter t with the letter x, and we're done. That's it. It's as simple as it gets. Don't think too hard. Evaluate this. Now, here's a problem. According to the fundamental theorem of calculus part 2, the lower bound has to be a constant. The upper bound must be a variable in order for this to be true. However, this problem has the lower bound as a variable and the upper bound as a constant. So before we can apply the fundamental theorem of calculus part 2, we must insert a negative so that we can flip the two bound around. Once we have accomplished that, then we can apply the fundamental theorem of calculus to find the derivative, to find this expression that equal